Welcome to The Explainer. Today, we're diving into a real-life case of mistaken identity, but not with people. We're talking about plants. We're going to see how some seriously cool chemistry can unmask imposters that are hiding in plain sight among some really valuable medicinal herbs. Okay, so let's start with the big challenge here. We've got this really valuable medicinal plant, right? But it's getting mixed up with its lookalikes, which are, well, pretty much worthless. And the crazy part? Telling them apart just by looking at them is almost impossible. So let's meet our main character. This is Phyllanthus neruri. It's a super popular herb, especially over in Southeast Asia. You know, it's often used in traditional medicine because people believe it's good for things like kidney stones. And because of that, it's a huge deal in the multi-billion-dollar herbal supplement industry. Right, so here's where the problem really kicks in. What happens when the plant you think you're buying isn't the one you're actually getting? Because, see, this particular plant has some really convincing body doubles out there. Okay, so our main plant, P. neruri, has a couple of common imposters, P. debilis and P. urinaria. And when I say they look similar, I mean they are practically identical. Visual inspection, totally unreliable. You can imagine what a massive headache this is for quality control. I mean, for a product to actually work, and more importantly, to be safe, you absolutely have to be 100% sure what's going into that bottle. So if our eyes can't be trusted, what can we trust? Well, the answer is to go deeper, like way deeper, right down to the molecular level. We've got to find each plant's unique chemical signature. This whole technique is called metabolite fingerprinting, and the idea behind it is pretty brilliant. See, every single plant species has its own unique cocktail of internal chemicals. These are called its metabolites. So this method captures that entire chemical profile all at once. It's kind of like creating a unique molecular barcode, or, a fingerprint for the plant. It's a dead-on way to prove its identity. So how do scientists actually get this fingerprint? Well, they use a technique called FTIR spectroscopy, and it's actually pretty straightforward. First, you take a dried leaf, grind it into a powder, and press it into a little disc. Then you shoot a beam of infrared light right through it. Now the chemical bonds inside that plant sample absorb the light in their own special way, and a detector measures all of that. What comes out is a unique spectrum. And that spectrum, that's the chemical fingerprint we're after. Okay, great. We've got the fingerprint. But, this brings up a whole new problem. The data we get back is unbelievably complex. So how on earth do you even begin to read it? So check this out. On the left, that's the raw data. It's just a total mess, right? A jumble of overlapping lines from all the different plants. There's no way a person could sort that out just by looking. But the goal is to get to what you see on the right, where every species is neatly sorted into its own little group. The big question is, how in the world do you get from that chaos on the left to that beautiful clarity on the right? The researchers themselves said it best. They basically looked at this and went, whoa, this data is way too complex. It's impossible for a human to analyze alone. You need powerful computer tools, they call them chemometric methods, to have any hope of making sense of it. So you see, the real challenge isn't just getting the data, it's finding the right tool to crack the code. And this is where things get really, really clever. To figure out the best way to decode this stuff, the researchers basically set up a competition, a bake-off, if you will. They pitted 4 different computer methods against each other to see which one could solve this plant identity crisis most accurately. Yeah, you can really think of these 4 algorithms as competing chemical detectives. Each one has a totally different strategy for digging through the evidence, those messy fingerprint files, to find the hidden patterns and point to the right culprit. All right, let's meet the contenders. First up, we have PCA-LDA. We'll call it the simplifier. Its whole game is to cut through all the static and noise to find the most important clues. Then there's SIMCA, the profiler. This one creates a standard profile for each plant, like a criminal profile, and then sees if the unknown sample is a match. Third, we've got neural networks, the learner. This is like a computer brain that actually teaches itself how to spot the patterns. And last but not least, GALDA, the evolutionist. This one is wild. It uses a survival of the fittest approach to zero in on the absolute most important data points to tell these plants apart. So, who won the battle? Let's look at the scorecard. This shows us how well each detective did at identifying the mystery samples. SIMCA, did okay, about 72%. The neural networks did better, getting up to around 87%. But look at the top 2. PCA-LDA and GA-LDA
Both of them nailed it with an amazing 96.3% correct classification rate. Wow. An impressive tie right at the top.
Okay, so we have a tie for first place. But here's the twist. The researchers still declared one of them the clear champion. Let's find out why. Let's just let that sink in for a second. 96.3%. I mean, that is an unbelievably high level of accuracy. It means that out of all those mystery samples, these top methods were able to get it right almost every single time. And the winner is Gilda, our evolutionist detective. So you're probably asking why. If it tied with the other one, what made it the champion? Well, the secret sauce was its efficiency. This is what blows my mind. While the other methods were looking at hundreds of data points, Gilda got that exact same 96.3% accuracy by focusing on just 6 key pieces of data. It wasn't just about being strong, it was about being smart. And here is the proof, right here. This plot is the beautiful after picture. Remember that chaotic mess of lines we saw earlier? This is what GALDA turned it into. I mean, look at that. You can see as plain as day how it took all those samples and separated them into 6 perfect, easy-to-read clusters, one for each species. It's the ultimate solution to the whole identity crisis. So, why does any of this matter to you and me? Well, it means we now have a fast, unbiased, and super reliable way to check if herbal products are the real deal. It's a game-changing tool for quality control that makes sure what's on the label is actually what's in the bottle. And that, of course, is huge for safety. It protects all of us consumers in what can be a massive and, let's be honest, sometimes murky global industry. And that really brings us to the final big idea. This ability to create and decode a unique chemical fingerprint, it's an incredibly powerful tool. We've seen how it can guarantee that a plant is what it says it is. So the question I want to leave you with is this. What else could we use this technology to verify? Think about it. Our food, our medicines, even the materials things are made of? The possibilities are pretty fascinating to think about.